You're going to
Good morning. I hope that you are doing well. So we have a nice day, sunny outside, so it's probably the best time to sit down and learn about Cayley's theorem. Yes. So, because this is also a very fantastic theorem. So if you really understand and you can follow what the proof of Cayley's theorem means, that you're really on the safe side when it comes to abstract algebra and conceptual concepts in mathematics in principle. Okay, so let me show you. Do you remember what was the content we just talked about that yesterday? So every group is isomorphic. In other words, in an unofficial way, means that it is a carbon copy of a group of permutations. So every group that you have is a carbon copy of a group of permutations. But let me remind you a little bit. So first, do you remember this notation? If X is not empty, if X is not an empty set, let's see. Yes. If X is not an empty set, do you remember I used this symbol for what? S sub X is the set consisting of all bijective functions from the set X onto X itself. So it was F, all the functions from X to X, which are 1 to 1 and onto. So I just want to remind you about this symbol we had before. And then I want to also remind you about the notion of isomorphism that we learned yesterday. So if I have two group structures, so let me say that I have group 1 with some binary operation on it, and I have a group 2. We say that group 1 is isomorphic. These two groups are isomorphic, and we write this symbol. If there exists a function, let me call it function f from G1 to G2, which is bijective 1 to 1 and on 2, such that what happens for every pair of elements A and B in the domain of the function, means group G1, what do I have? F acting on AB is equal to F of A acting on F of A times F of B. So, and then I will not differentiate between binary operations from now on. So when you see AB, this multiplication means the binary operation from group G1, because A and B are chosen from G1. So when I multiply them, I'm multiplying them based on the binary operation on G1. But when I go to the right-hand side, F takes elements from G1 and gives me elements in G2. So if I ask you where F of A is from, F of A is from G2, the same reason F of B is from G2. So this multiplication is not the same multiplication here, it's the binary operation on the second group. But from now on, you need to learn it from the context. So this is the way you see it in algebra books. So if this happens, these two groups are called isomorphic. Essentially, it means one of them is a carbon copy of the other one. And if you are more comfortable in studying one of them, you can study one of them, and then whatever results you get from that, you can immediately transfer them into the other. So that's the idea. Okay, but this Cayley's theorem is a very big claim. So it is claiming that any group in the world, even if it's not discovered yet, it will be isomorphic. It will be a carbon copy of a permutation group. Okay, so now we want to go to Cayley's theorem. So first of all, so it means that a group G is given, G a group. We want to prove that G is isomorphic to a group, if you want, consisting of permutations. permutation. So let me just write like that. So this is what we want to show. Okay, so it means that if you imagine this is your group, it consists of some elements, for example, element A, element B, and etc. And then we want to show that this is isomorphic to a group of permutations. Usually when you want to show that two groups are isomorphic, you should have the groups in place and then try to find the bijective map from one of them to the other one that preserves the binary operation. Okay, so it means that in this problem, we only have a group. For isomorphism, we need two groups. So it is written in words, isomorphic to a group of permutations, consisting of permutations. Okay, but the first thing comes to mind is probably we can find an isomorphism between my group and S sub G. Because if you have a group, it means you have a set in place. And whenever you have a non-empty set in place, you can talk about the set of all permutations. But do you think this is a good candidate? So in principle, what I want to write here is that SG, what does it mean? SG means I replace X with G everywhere. All the functions from G to G, 1 to 1 and on 2. And of course, you know that always the binary operation is the function composition. This is the group of permutations, but it is the group of all possible permutations. Do you think it is a wise decision try to establish an isomorphism between G and SG? Because if we could, we are done. It's the group of all possible permutations. But do you think it's a wise decision to go for it? Is it a wise decision to try to establish an isomorphism between G and the totality of S sub G? Is it a good idea to look for it or not? Why not? The answer is no, but why no? Yes?
Wouldn't it be, that would be the group of all binary operations on G, right?
No, it will be the group of all bijective maps from G onto G.
And wouldn't that be equal to, wouldn't that represent the group of all binary operations acting on G?
No, not all the binary operations. It is representing the set consisting of all bijective maps from the group to the group. Okay? If I'm telling you that the Cayley's theorem is a little bit vague in its wording, yes? It says that your group is isomorphic to a group of permutations. This is already a group of permutations, but a special case. It contains all permutations. But my question is that, is it a wise decision to go for it? Yes, please?
I think we want to do it the other way around.
No, it doesn't matter the other way around. Okay? Yes?
I think we only need one element of SG, not all SG.
No, I mean, my question is that, is the wise decision even to sit down and try find a one-to-one correspondence that preserves the operation from G to S sub G? Yes?
All we need to do is find a group of permutations. We don't need to find the group
Okay,
of every single
but we should have a candidate. The theorem tells you that if you pick a group, this group that you have picked, no matter which one is it is isomorphic to a group of permutations. Yes? If I ask you, do you believe that what I have written here is a group of permutations? Yes or no? It is a group of permutations. Okay? So one possibility is that, because this is the only thing that I have in my hand, might be you want to go for this. If you, of course, can establish this, you are done. Cayley's theorem is proven. But my point is that this is not even a wise decision to go for it. And there is a simple reason for that. Yes, please.
It has more elements.
Exactly. Thank you very much. Because in general, let us say that G has 3 elements in it, A, B, C. So the order of this group is what? 3. And if I ask you for this set, what is the order? So let me write it with a different color. So if I give you this set, A, B, C, and if I write SG, means the set of all permutations from this 3-element set to itself. And if I ask you what is the cardinality, what is the order of this group, what was that? It was 3 factorial. Yes, so it is 3 factorial, and that is 9. Sorry, it is 6. So there are 3 elements here, there are 6 elements here, so there is no way that I can establish a one-to-one correspondence, let alone that I need an extra condition on top of that. I cannot even find a bijection. Is that clear? So that is not a wise decision. These questions I'm asking because I want to deepen your understanding, okay? So this is not a wise decision to go for it, okay? So it means that I need to give up my ambition and try to find a subset of this, which is a group of permutation but not the whole package, so that it becomes isomorphic to the group that I have. So that's the idea. Is that clear? This theorem carries a name of a mathematician. Usually it means that this depends on the genius of the person. So, but what I want you to understand is to follow me, and if you really can understand every step, it means that your algebra are on the safe side. Okay? So, what does it mean? The first thing I want to do is a little bit strange. I am trying to actually copy his proof, so you should be a little bit patient. You might say, Babak, why do you think this is a good way to go? I'm not, I'm just following Cayley, okay? But I want you to understand why it works, okay? So, what we want to do, we want to do that. If I want to give you a diagram, so if I want to draw G here, I mean, SG is much bigger. Yes, so there would be no way that I can establish a one-to-one correspondence here. But I want to go for a smaller piece of it in a wise way so that I can guarantee that this piece is isomorphic to my original group. Is that clear? Okay. So now what we want to do, I pick an element from here. Okay, so just think in this way. I pick one element from my group, and I want to define a function for you, which I call it, I'm following your book so that you are not confused. Piece of A, define it in this way for you. Okay, this is actually the genius of Cayley. He came up with this function. Okay, so momentarily forget about the Cayley's theorem. Concentrate what I am talking about now. What I did, I just picked one random, an arbitrary element from my group, and I am defining a function for you from the group to the group by this rule. And I am calling that function, I could have called this pi, f, g, h, whatever you want to call it, but that is not a good name. I want to connect this function to this picked element. So somehow I have to put this in the name of my function so that I can see the connection. So don't let this index confuses you. Okay, so this is just if you want, you can write it here. But if I write it here, no one can see that this pi is related to this picked element. So that is why I choose piece of A, so that you know that this function that I am defining is for this particular element from my group. Okay, but forget about everything. Let us discuss about this function. My question for you is that, do you think that pi A belongs to SG? So I want to make sure that this pi A lives here. This is my goal. I want to show you that P of A is within this bigger set. So how should I prove it? I have to show that this is a bijective. Is that right? In order to show that this is a bijective, I have to show that this is a one-to-one and onto. Okay? So injectivity of pi A. So what is that? Let us check. So I would say that let x1 and x2 belongs to G such that pi A acting on x1 is equal to pi A acting on x2. Yes? We show that what? Complete it for me. We show that what? Injectivity. We show that x1 is equal to x2. Yes? Okay, so let us do that. This is my assumption. I want to confirm that. Now you see that this is extremely simple. I want you to feel that this is not a circular argument. You just wait for it. Okay, so pi a acting on x1 is equal to pi sub a acting on x2. So pi sub a acting on x1, I use the formula that I defined for my function, so it becomes a times x1 is equal to a times x2. Okay, so can I conclude that x1 is equal to x2? Yes or no? Yes, because that's cancellation law. Cancellation law from the left. A and x1, A and x2 are within my group. These are my group elements. And then I know that this is happening, and this is on the left, this is on the left. So I can cancel from the left. Cancellation from the left. So this means that injectivity is done. So surjectivity. Okay, I want to show that pi sub a is surjective. So how should I do that? I would say that, let me write it once for you. Let y be in G. We show that. Can you complete the sentence for me? We show that, let me write the first part. There exists, and I want to wait for you. I want to prove the surjectivity of my function. I pick any arbitrary element from the right hand side, and I guarantee we show that what? There exists, yes?
An x such that
An x where?
in G. In G.
In G, such that,
A times x. AX.
now let us write it with function. Pi a acting on x is y. This is what I want to show. That's the meaning of surjectivity. Okay? So you can go to a scratch paper and find your candidate, or be genius and just guess it. Okay? So let us go to the scratch paper here. Y is given to me. I am looking for such an x that is sent to this particular y by the action of p sub a. So what does it mean? It means p sub a act on x, it should be y. In a scratch paper, I see that this is just a x is equal to y. But remember, y is given, a was already given, you are looking for x. So what is x? X is a inverse multiplied by y. Is that right? Okay, so we show that there exists an x in this such that this happens. So claim. So this claim comes from this scratch paper work. So claim a inverse x is sent to y under pi of a. This is my claim, and if I can prove it, we are done. But of course, you have to be careful. This is indeed in G. Is it? Yes, because a was in G. G is a group, so a inverse is in G. X was chosen from G, and G is closed under multiplication. So definitely this belongs to G. But is that correct or not? Let us check. I am claiming that this element, which is in G, is sent to that chosen Y. So in order to guarantee this, I have to do the application. I apply P sub A on this claimed element to see what happens. Yes? So let us do that. Can you help me to do this? P sub A is acting on an element. P sub A multiplies the input from left by this picked A. Yes?
Shouldn't it be A inverse Y instead?
Ah, yes. Thank you. Thank you very much. This was P inverse. This is A inverse Y. Thank you. Okay, so I am acting this on here. So what is the answer? The role of P sub A is multiplication by A from left. So the input is this guy. So this function will multiply the input by A from the left. So it becomes A inverse Y. Yes? But now, you know we have associativity in a group. So I can write it like this. And then this becomes EY. and this becomes y, and weird. So I was able to prove my claim. Yes. So this function is not a random function. It is definitely a bijective function. So this is done. Now this question mark is answered to be true because I showed that this is injective and surjective, so it is bijective, and because it goes from G to G, definitely P sub A lives there. Okay? But now can you feel the correspondence? So what we want to do, I want to pick another element B. So what happens? Then I will define a new function for you, but instead of having P sub A, I will have P sub B, pi sub B, and then what do you think I will define pi sub B? Pi sub B will be Bx, pi sub C will be Cx, yes? So, and then I have pi sub B here. And then so I will pick one element at a time from G. Using this idea, I will have a bijective function in SG. So when I do it for every element in my group, I will have a bunch of bijective functions here. Yes? And now if I circle them around, yes, it becomes a subset of the bigger set. And something is already clear. There is a one-to-one correspondence between my group and that one. Because if you give me A, I immediately can give you P sub A. You give me B, I give you another P sub B. Of course, I have to prove it, but intuitively it is clear. The number of elements here and the number of elements there in this smaller piece match. So it's a good candidate for having a one-to-one correspondence. So the problem of the order is not relevant. I just want to give you the general picture. Is that clear? So in principle, what that means, let me write it with a different color. So here, for example, you have G, A, B, I don't know, C. At some point, you have A, B here. At some point, you have B squared, C here, you know. This is a group, so it should be closed. And then you have this, okay? This is the way that you have to think. So then you have another set, which is pi sub A and pi sub B and pi sub C, and then you continue, you have pi sub what? AB, yes, very good. And then you continue, you have pi sub B squared C, and etc. So that is the way you have to think. It's just intuition. So it means what I did, I have a group. These are my elements. Every multiplication will be in my group because it should be closed under binary condition. And for every element here, I defined a bijective for you. Is that right? Now what I want, so let me, if you don't mind, let me call it A. So is A a group of, is A a set of permutations or not? It is a set of permutations. Why? Because inside A, you see permutations. You see bijective maps. But it is, on the other hand, I know that the number of elements here and the number of elements there match. So it means that it is a good candidate if it is indeed a group. So this is something we want to prove, okay? So I would say let A be defined to be all pi A's, which we defined up there, such that A belongs to G. Okay. We prove that can you tell me what I'm going to prove based on your intuition?
That it's a group, right?
I want to prove that it is a group. It means that I want to prove that it is a subgroup of SG.
Also
Okay.
not a theorem. That every subgroup is also a group. For the
Oh, we don't know. We know it's a subset. I have taken some elements from here and I have constructed these functions and I have put them in a bag.
Yeah.
This bag has the structure of being a subset, but I'm claiming more. I want to say that this is a subgroup as well.
Sorry.
Is that understandable?
Yeah.
So we proved this and the surprise of Cayley's theorem. What do you think? And We want to prove Cayley's theorem. So this, if I can prove that, yes, and
But A is isomorphic to G.
A is isomorphic to G. Yes, so I would write G is isomorphic to A. Okay, so these are the big question marks. If I can do that, I am done. Because Cayley theorem tells me that any group that you pick some G is isomorphic to a group of permutations. That is what I want to do. Okay, but before continuing, I think this would be better if I give some useful statements for this function. I want to know these functions a little bit better so that I can use those properties to be able to finally prove this. So I would say that useful statements regarding high A's, yes? Something like this. So statement number one, and by the way, here, can you tell me, do you think A is empty or not? Because one of the things that we want to prove for a subgroup, being subgroup, is that we should prove that A is not empty. And usually we check that if the identity element of the bigger group is there. But by construction, do you think that A can be empty? No. Because I picked one element here, whatever it is, and I constructed one single function for you, and it is there. So there is no way that this becomes empty. Okay? Is that clear? But let us just go a little bit further. Now my question for you is that, do you think the identity element of SG will be here or will be left outside? Yes? Do you understand the question? Because the identity element of G, what is the identity element of G? Do you remember? We denote it by ID sub G, which goes from G to G, but assigns every element to itself. Yes? ID of X is equal to X for every X. So ID is, of course, a permutation. It might be here or might be inside. But my claim is that it is inside. Yes? Anyone? Anyone else? Why do you think the identity element should be inside of this set? So what does it mean? You see, A is going to P sub A. B is going to be pi sub B. It means that there should be something here which is mapped to IDG. If I can find something here which is mapped to IDG, it means IDG is inside, not outside. But can you tell me what this question mark should be? Yes?
Shouldn't it be the identity?
Very good. The identity element. So what is the claim? The claim is that identity G is just pi A. Pi E. Is that right? So how can I prove this claim? Very simple. I apply pi. If I want to prove this equality is between two functions. If I want to prove two functions are equal, I have to confirm that the domains are the same, which is the case. The domain of this is G, and the domain of this one is also G, based on that definition. And one more thing, I have to confirm that when I apply IDG on X, and when I apply pi E on X, they give me the same results. So tell me, if I apply ID sub G on X, it gives me X by definition of the identity function. And P E sub X gives me E multiplied by X. But E multiplied by X is also X. So, and they are equal. So that's it. Yes? So IDG, the identity group element of G, SG, is actually pi sub E. That's another name for it. So it is there. So number two. Number two is that, so I want to show this is the case. If I have pi A in A, and if I have pi B on A, Okay, so I am choosing two elements from A. And my question is that what can I write for P with index AB? Oh, sorry. What can I write with the multiplication of them? So you see what I'm doing? I am taking two elements here. Multiplication here means composition of functions. I know that the composition of these two functions is another bijective. So if I take two elements from here and I multiply them, it is already guaranteed that this is in SG. But I want more. I want to make sure that it is in SG and of course inside this smaller piece. And you see why?
Isn't that what you wrote before?
Not exactly. So what is PA, PB?
No, isn't it? Or am I wrong? Is it not just the part above the line?
No. That we don't know the isomorphism yet. We haven't even gone to that. So I just want you to understand that pi A multiplied pi B, my claim is that this becomes equal to, yes, can you tell me what's the answer?
It is equal to pi a of pi b x, which is just pi ab.
Pi AB. This is what I want to prove. Okay, so let us check. Again, I want to prove this equality. This equality is between two functions. If I want to prove two functions are equal, I have to confirm the domains are the same, which of course for both of them the domain is G, and I have to go more. I have to show that any element from group that I choose, this acting on that element is equal this acting on that element. So in order to prove this, I would say that let X belongs to G, we prove that pi A, pi B acting on X is equal to pi AB acting on X. If I can prove this, then of course means that these two functions are equal because they are acting the same way on group elements. Okay, so let us do that. Proof of the claim. So I will come here and write pi A, pi B acting on X. This is composition of two functions. This is after this one. So pi A has to wait so that pi B acts first. And then when the result is clear, then pi A can act. But can you tell me what is here? So I keep pi sub A for the time being. I want to do this one. What is the answer to pi sub Bx? Bx. Okay? And now, what is pi sub A? Pi sub A is the multiplication from the left by A. So this will give me A times Bx. Yes? And because of associativity, I can write it as ABX. And if I want to write to this one acting on X, what is the answer to this one? This is multiplication by AB from left. Yes? And they are the same. So this means that if you multiply, multiplication here means composition of functions. If you multiply pi sub A by pi sub B, it gives you pi sub AB. Okay, so it means that if pi sub A is in A, pi sub B is in A, pi A times pi B, because it becomes equal to pi sub AB, it belongs where? To A. Yes? Is that right or not? Are you following? Okay, so now this is the case. And then one more thing, one useful statement, let me write it here, number 3. What do you think will be number 3? Something about inverse. So you should have an educated guess. So I want to say that if pi A belongs to A, okay, so what I can say, what is your guess about the inverse of this function? First of all, is this function invertible?
Yes.
Yes, because it is in A, and A is within G, so it is bijective. Bijective is invertible. So my claim, so I am picking one element from A, I am trying to show you that its inverse is still within A. Okay, so how can I prove this? How can I prove this? What do you have any guess? So you should have a guess if I want to prove. What is your guess? The inverse of pi A. So what I am saying is that you know A goes to pi A. My question is that which element do you think it will go to this? It will go to this one. Yes. So I actually wrote the answer. Yes. So it becomes pi A inverse. That's what we want to prove. Yes. And then how should I prove it? I mean, it's very simple. Either you can start from scratch or you can use the previous one. For example, can you tell me what is the answer to this one? Yes?
QE.
Why? Because we just proved pi sub A times pi sub B is equal to pi sub AB. So this becomes equal to what? Pi A inverse. Yes? And what is this one? It's pi E. But do you remember what was pi sub E? It is the first statement. Pi sub E is IDG. And I hope that you agree the other way around is also true. So this means that I am composing these two functions. In any case, the answer is the identity element. So it means that these two elements are inverse of one another. Okay? So this means that we have proven this. Do you see what I have done? So here, the inverse of this is proposed to me. I confirm it is right by showing that if I multiply them in any order, it gives me the identity. Is that clear? So we are a little bit relieved now. So this is not just a subset. It is more than that. It is a subgroup. Is that clear? Because it is not empty. It is closed under multiplication. And it is closed under inverse. Yes, because this belongs to A. Okay, let me just wait a little bit. Are you following or not? Is it clear what we are doing? So we tried to be a little bit creative. I mean, Cayley did. It was creative to find a set that can be put in one-to-one correspondence to my original group. And he showed that the way he did it, has a structure of group within it. But are we done or not? I'm just following your memory now. I'm just trying to. Are we done or not?
You have to prove isomorphism.
Isomorphism is left. So, but we have our candidate. So this part is done. This part we should check. Okay? We want to show that this subgroup that I finally was able to construct is isomorphic to the group that I started with. Okay? And if you are following, you can do that yourself. And I'm waiting for you. So if I want to prove this, so let me write it here. So if I want to prove that, we want to prove that this is isomorphic to A. To prove that these two groups are isomorphic, I need what? I need a bijective map from one of these groups to the other so that it also respects the binary operation. That part is the hard part, to come up with a bijective map that also respects the binary operation. But I would recommend you first think about establishing a one-to-one correspondence and pray that that one that you found is the correct one. Yes? So you have to have some instinct in algebra. Okay? So now I would say that if you're following me more or less, you should be able to actually propose me the bijective map so that hopefully it turns out to be our isomorphism. I want to give 30 seconds to everyone. So please write it down yourself. Can you write something down on your paper? As a candidate for, how do you say, allegedly, how do you say it in English? I mean, a candidate for your isomorphism. I want you to write it down. So what you need to write down, you need to write a function. From where to where? For example, from G to A. which is bijective, and hope for the best that this will give rise to the isomorphism. Okay, how many of you could? Raise your hands. Okay. If you couldn't, let me give you a hint. It's already on the board. Let me draw something here for you. Yes. It's already on the board. It's a one-to-one correspondence between those group elements and the ones we did. Yes? Okay, now, but this is it. But you have to write it in a formal way. Can you write it for me? So, whenever you are genius, you need to write claim. We show that, I'm waiting for you. We show that what? The function. Okay, can you complete it for me? The function, so let me call it psi.
Psi of x from G to A.
From where to where first?
G to A.
G to A. The function such that, yes, completed, or defined by. It's better.
Psi x equal to pi
Yes, psi
of x.
of x acting. So you cannot say psi x is pi x because psi.
Psi parenthesis x is equal to.
Ah yes, this one. Yeah, that's correct.
Equal to pi.
Pi sub x. Defined by, you don't need to write that. Defined by this is an isomorphism. Yes. But because I have used, so might be x is good. But do you see that? That's exactly the same correspondence that we got the intuition from that picture up there. Yes? So we already know that this is a one-to-one correspondence. What we want to show is that really respects the binary operation. So is an isomorphism from G to A, something like that. So we show that the function defined by this is an isomorphism. So what does it mean? It means that if you pick one element from G, I give pi sub x, which was defined up there for you for any arbitrary group element. Is that right? Okay, now I want to prove this is isomorphism. What should I prove? 3 things. The first, it is, say it. It's bijective means it is one-to-one and onto, and it preserves the operation. Yes? So one-to-oneness is more or less clear. Yes, because we have done that. But if you insist, so if I want to prove that psi x, if I want to prove that psi is bijective, let us do that together. Let me write it here. I want to show that psi is injective. So what should I do? I would say that pi x1 is equal to psi x2. I have to confirm that x1 is equal to x2. And by the way, let me do it properly. Okay, so this is what we want to show. This is a question mark. Where are x1 and x2 are coming from? x1 and x2 are coming from G. And I want to prove this. Why this is true? Why equality of psi x1 equals to psi x2 guarantees the equality of x1 and x2. Let us do that. You are telling me that psi x1 is equal to psi x2. By the way, it's not trivial. So, what does it mean? It doesn't mean x1 is equal to x2. It means what?
Pi x1
Pi sub x1 is equal to pi sub x2. Okay? So in other words, I want to make sure that no two elements of the group goes to the same. Yes? But so it means it is not finished yet. This is 100% correct because of my definition, but I want to go one step forward and conclude that the indices should be the same. So how can I do that? How can I do that?
all element in G.
What?
For all element in G.
So when you say, what is this? This is a function.
Yeah.
What is this? This is also a function. When I say two functions are equal, it means they act the same on every element, but one element matters for me here. Which element? Very good, very good. So you are developing here so you can be an algebraist, yes? So pi sub x1 becomes equal. So this is, no one can ask why. Because if two functions are equal, this equality is not between two numbers, this equality is between two functions. If two functions are equal, they act the same on every element of the domain, including E. Okay? But now tell me, what is P sub x1E? What is P sub x1? P sub x1 is multiplication by x1 from the left. So it becomes x1E. And what is pi sub x2? It is multiplication by x2 from the left. So then it means that x1 is equal to x2.
Yeah, but you can actually write an element, then use cancellation as well.
No. So what do you mean exactly?
If I got like a pi x1 of A.
Yes, but that's not a good mathematical way of doing things. Yes?
Why?
No, it's not a very good thing to do. Because if you can say that I pick one element, whatever that element is. Usually mathematicians don't do that. They pick a particular one if they don't need a general idea. So the way that you are doing is good for guessing that, but here you say that it doesn't matter. If I write it for any A, I can write it as x1A, and then I have the cancellation law from the right.
Yeah.
And it gives me. But you have to write it. You know, you have to write let, and I told you that this is a very good reason. Mathematicians are lazy. So if you write this, no one will ask you what E is. But in principle, if you want to write an article, and if you say that pi x1, before that, you should say let A be a group element, then this. That's why. But by the way, that's correct what you're saying. Yeah, because this is my mindset, so I didn't think in that way. Any questions? Yes?
Because doesn't this have to be true for all elements and not just the identity?
Yeah.
So that's what he asked. Yes? You can do that, but you have to stop here and then say, now let A be a group element because these functions are the same, so they are acting on the same. But if I write this one, no mathematician will complain. Because you are saying that two functions are the same. No, be careful. You don't want to prove it in totality of it. You just want, you know this. So you know that the functions are equal. You have something very general, but you want to conclude something particular out of it. And that is the equality of exponents. Yes, we don't want to prove it in totality. Do you understand what I mean?
Yeah.
Okay. So, this is it. And now surjectivity. Okay. So, because we are running out of time, I want to leave surjectivity to you. Surjectivity is more or less very trivial. Okay. So, psi is surjective. I do something helping Cayley, okay? So surjective. So I want you to do it yourself or convince yourself that this is true. But the last part, still it is not done. We want to do it and then we have the break. So what should I do finally? So I want to show that this is an isomorphism. I have to show it is bijective. Injectivity is done. Surjectivity is on you, which is very simple. One more thing. We have to show that
All A, B.
it respects the operation. So it means that the last part is that I should prove what? I should prove that if x and y are from G, I want to convince myself that psi, tell me, what should I write?
Psi,
Psi of xy, what is this xy? The binary operation of G is equal to what?
psi x.
Psi x multiplied by psi y. What is this one?
Psi x.
This operation is?
Oh,
This operation is
function computation.
function composition. Yes? So we have to check this one. Okay, so let us do it. So I would say that you help me. What is psi of xy?
Pi xy.
It is pi, according to your definition, it is pi, but equate with this as an index. This is psi x and y. Yes? And if I ask you what is psi x, psi y, what do you say? Psi x, psi y, psi x is pi sub x multiplied by pi sub y. Yes? But what was it?
Pi xy.
We had it somewhere here. Pi sub a multiply, it becomes pi ab. Yes? So this becomes pi xy. So the left hand side is pi equate with xy as the index. The right hand side finally becomes pi equate with psi xy index. So they are equal. Yes? So these two are equal. So this is the proof. So you see, it was not hard. So the only thing you have to always contemplate what happened. So his genius was to come up with those pi sub a functions, which, by the way, was extremely simple function, multiplication by left. And he was able to cook up a subgroup of the bigger set so that it can be put into one correspondence in an isomorphic way with your original group, no matter what the original group is. Is that clear? Are you excited or not? Okay, so you should love it. You should feel it, okay? So now we can have a break, thank you, and then we come back again. And by the way, the classes are on the schedule now, the extra lessons, okay?